We're still a bit short on compact spaces, so let's do something about that. Well, the first thing that's a bit annoying is we don't have a statement for closed and bounded subsets of Rn, right? So we should be able to say a compact subset of Rn is compact if and only if it's closed and bounded. That makes, we should be able to prove that. We're going to get to that through the observation that Rn is R cross with itself n times, right? So we want to think about, if I take compact topological spaces, is their Cartesian product compact? We want to discuss the disjoint union. We want to discuss the quotient, so that we know that the usual constructions I've outlined for topological spaces preserve compactness. So I'll start with the quotient. Well, I wrote down an argument in the notes, but it's a bit silly given what I just said, actually. All right, so what's the quick argument that the quotient is compact? So here, tilde is any equivalence relation on X.
The quotient map is continuous?
Yeah, right. So the image is compact and the image is everything. So. All right. So what I wrote down in the notes is just the special case of that argument repeated. Don't know why I did that. Okay, so the quotient, any quotient of a compact space is compact. In particular, well, this is compact. Right? S1 identified as, we know the interval is compact because it's sequentially compact, and then the quotient is compact by the lemma. Of course, we'd also like to deduce that from the fact the circle is a closed and bounded subset of R2, but we don't actually have that statement yet. Okay, but that would be another argument. So let me do the product. So it suffices to prove an open cover which is taken from the sort of standard basis for this topology as a finite subcover. So we take an open cover consisting of Cartesian products of open subsets ui of x and vi of y. All right. So we just pick a point in x. As I said last time, if x is empty, then this is trivial. So just choose any point in x. Well, this is a subset of x cross y, and therefore a subset of the union of these sets in the cover, because, well, that union is everything. But this space, so you can check if you take a singleton and take the Cartesian product with any space, the result is homeomorphic to that space. Taking the Cartesian product with a singleton doesn't do anything. So if I take this space and take the Cartesian, well, that's homeomorphic just to y, and y is compact by hypothesis. Now, compactness phrase for y is about y as a space on its own, but it's this being compact as a topological space on its own is equivalent to this condition I discussed last time of if there is a cover, in the sense this is contained in a union of open sets, then there's some finite subset in which it is contained. So there is, depending on x, a finite subset Jx with this inclusion, all right? So that's using compactness of Y. All right, but there's finitely many of those J's. So what we can do is we can define Ux dependent on X to be the intersection of all the Uj's. That's a finite intersection, so that's open. And it contains X, right? Because this inclusion says that X is contained. Well, that inclusion doesn't say that X is in every Uj, it just has to be in some Uj, right? But if X is not contained, I mean, if there's a J in Jx for which X is not contained in Uj, well, then you didn't need it, right? Because then the left-hand side would have been contained in the union without that J. So we may as well assume that X is in every Uj, throw out the ones for which it's not true. Okay, so that means that X is contained in the intersection of all the Uj's. Well, then it follows that Ux cross Y is contained in the same union. Now, why is that? Well, take something on the left-hand side. Suppose it's of the form T comma Y. Right? So T is in all the Uj, and Y is just any point in Y. Well, xy belongs to the left-hand side, right? Take the same y and look at the pair xy. That's on here. And therefore, it belongs to uj cross vj for some j. Well, that means that y is in that particular vj. And while t is in everything, so ty is in the same open set. Okay, so this inclusion holds. So we haven't used compactness of X yet. Well, we've constructed an open set for each X which contains X, so all of them together cover X. And X is compact, so there is a finite subcover ux1 up to uxn, say. All right. Well, then X is equal to the union over all x's of ux cross y. Right? Because every x comma y is in, well, ux cross y, for instance. But those, I have this expression here, so that's contained in the union. And here I'm allowed to take just the cover. That's the point. Okay, because every point in X is contained in one of them. And then replacing uxi cross y by this union, so that's the union of j in jxi, uj cross vj. Well, but that union is finite, and per I, there's only finitely many elements j in jxi, so that's a finite union of things in the basis. So we're done. Okay, so x cross y is compact. All right, so theorem. All right, so I think you've all sort of seen this statement before. So how are we going to deduce it from what we've got so far? Well, the main point is that for any A and B, we know this is compact. So by the aborted lemma, the Cartesian product of a compact space with itself n times by induction is compact. Okay, so that's what we're going to go on. All right. So if the subset is compact, so A compact implies A sequentially compact. Right, the subspace topology on A is the topology associated to the metric, the restricted metric from Rn. Okay, and we know that compact implies sequentially compact. And then, this direction is just the same as in Bolzano-Weierstrass. It's literally, I'm not cheating you by saying that. It's just the same argument. So what does closed and bounded mean? Maybe I should say, so closed, well, it's clear what that means. A subset of a metric space is bounded if it lies in some ball. Right? When I said the definition in R, I said a subset is bounded if it lies in some interval of the form minus m comma m. Right? In a generic metric space, there's nothing, there's no reason to center it at some special point 0, and there's no reason really in R either, if you think about it. So a subset of a metric space is bounded. So X is a metric space. If there exists a point and some epsilon such that y is contained in that ball. Okay. Now the argument that a sequentially compact subset of Rn is closed and bounded is just the same as what I gave when I reviewed that proof. Okay, so this direction then is okay. And then in the reverse direction, so here's where we actually use what we've been up to. Well, since A is closed and bounded, the fact that it's bounded, well, it's in some ball, and if you think about it, that means I can sit it inside some Cartesian product of a fixed interval with itself. All right? Okay. But any closed subspace, okay, we know this is compact, as we just discussed, but any closed subspace of a compact space is compact. Okay, I've left that as an exercise in the notes. That's straightforward, right? So if I have a space and something sitting inside it, if the space is compact and something sitting inside it is closed, then you take an open cover of that closed thing, throw in the complement. That's an open cover of the whole space that has a finite subcover, and, well, that must be a finite subcover of the original closed thing. So a closed subspace of a compact space is compact. Well, so we're done, right? So A is a closed subspace of this, that's compact, so therefore A is compact. All right. So we can also maybe do this part using more purely topological methods once we get to the concept of Hausdorff spaces. Okay, so what I want to do quickly in the time that's left is, okay, so at least we know that closed and bounded subsets of Rn is compact. That's a respectable supply of compact spaces, but let's do a little better than that. So okay, so any finite CW complex is compact. So recall what that means. That means that X is built up iteratively by attaching cells. So there's a sequence of spaces where X0 is a finite discrete space. So that's a finite set with the discrete topology, the topology where everything is open. And for I greater than 0, there's a push out of this kind. Okay, so there's some diagram that looks like that, which constructs xi from xi minus 1 by attaching some number of I cells. Okay, so I claim X is compact. We'll prove that by induction on the construction of the fixed X. So start with the base case. X0 is compact. Well, X0 is finite, right? So if I have an open cover, certainly there's a finite subcover. Right. And moreover, it's a good exercise to check that a discrete space is compact if and only if it's a finite set. Right? Okay, so X0 is compact. If xi is compact, that's the inductive hypothesis. Well, what is, sorry, xi minus 1? If xi minus 1 is compact, then first, I mean, xi is a quotient of this. I know quotients of compact spaces are compact, so I just need to show this is compact. This part is compact. The disk, well, the disk is a closed and bounded subset of Rn, right? So this is compact by Heine-Borel. This is compact by hypothesis. And then a finite union, so this is a finite index set. If I take a finite union of compact spaces, the result is still compact. Because if you took a cover, each individual thing would have a finite cover. Just take all those indices together. That's a finite union of finite sets. So that's a finite subcover. All right. So a finite disjoint union of compact spaces is also compact. then xi, which is the quotient, is compact by what we said earlier. Continuous image of a compact space is compact. All right, so then by induction, xn, which is x, must be compact too. Okay, so anything you can construct by adjoining cells will be compact.